continuing on beams. In the Okigbo classes, we are continuing on continuous determinate beams. Continuous determinate beams. Most continuous beams are indeterminate, but beams can be continuous and still be determinate if we introduce hinges. If you watch this beam A, B, E, F, C, D, you will see that at point E and F, two hinges are introduced because to make the beam determinate, the introduction of those two hinges make the beam determinate. So to solve this beam, what we have to do is to divide the beam at the points of the hinge, of the point of the hinges, we divide the beam. Because at the point of the hinges are points of flexibility. There's no resisting bending moment. We can break the beam there without having problems. It is where there is rigidity, where there is stiffness, that the bending moment occurs, and if you break it, you have to calculate those bending moments there. But here, there's no bending moment because of flexibility of the hinges. So now we cut at the hinges. The first cut we did was to cut at EF. We cut at EF. Look at the EF. Brought here. Cut. EF. We cut it and bring it out. Why we had to cut at EF is that if you look at it, the most unstable part of the beam, if they are cut, you will see that is EF. So we cut EF and load the EF on the other two parts of the beam that are more stable than EF. If you watch, CD and AB are more stable than what is holding EF is just the hinges. So the two will be loaded on the most stable part of the beam, and that's exactly what we have done. Look at it on the breakage, and it's lying on both of them. Is sitting on both of them, but either CD or AB is lying on them. So now that it's sitting on them, as you can see exactly what is here, is what they are, except that it is broken here to show how EF sits on AB and CD. So with that, I can now separate that EF and solve it. If I solve it, after solving it, the reaction I got at point E, I load it on AB, at the point of E on AB. After that, the reaction I got from EF at point F, I load it on CD. That is it. I load it on CD. So when I load it on both of them, and on AB and on CD, I solve AB. I solve CD. Then I've solved the whole beam. What I meant by solving it, I will get more of the reactions on the components of the beam and get the bending moments on the components of the beam and get the shear force on them. If there are normal forces, I do the same thing, but because of the nature of the loading here, the normal force is not there because the loads are straightly vertically pressed, that they could not generate normal force on the beam. So the shear force, the bending moment, the reactions generated will be calculated component by component. That is what the introduction of the hinge has done by making the beam determinate. So I move on. Now to move, I take the simplest one first because I need to do it first so that I can get reaction from it to load on the next component. Because if I don't do it, I won't get the reaction I will load in the component. So I deal with EF. So to deal with EF now, I say to get the reaction at E, as a total moment about F is equal to 0. I start 5 ROE, because the distance ROE is 5 meters from F. 5 ROE minus 8. 8 times 3, because that's the distance from E. That's from F. It's equal to 0. That means ROE is equal to 8 times 3. Happen to be 24. 24 over 5. 24 over 5 is 4.8. 4.8 kilonewtons. That is the reaction at point A. Look at it, that's why I load it. 4.88 kilonewton, I load it, that is it. I load it now on AB. So I now try to get the reaction at F. I say to that moment about E is equal to 0. Have 5 RF. RF minus 8 times 2. Take moment about E equal to 0. What means RF? 8 times 2. 8 times 2 is 16. Over 5. Which is 3.2. 3.2 kilonewton. Look at it. I load it. I load it on CD. I load it on CD. Look at it. I load it on CD. So I can now conveniently have finished. Okay, I can get bending moment. Let me get bending moment in here in EF. So if I call here, I have which one? I have. Let me call here G. This point is G. So moment at G is equal to moment at G. That's RA now. That's RE, which is 4.8. 4.8 times the distance, which is in this case is 2. 4.8 times 2. That's the moment at E at G, which is 6. 2 is 8. That's 9.6 kilonewton meter. That's the moment at G, 9.6 kilonewton meter. So now I have dealt with EF. Now, so I can now take any of A, B, or C, D and work because the load on it has been harnessed from EF. Look at it there. So I take the AB. I have dealt with EF. I've gotten the reaction. I've got the bending moment. And the shear force is the reaction. So now let me deal with AB. So I start. I want to get the moment. I want to get the moment that I want to get the reaction. Sorry, at A. So to the moment about B, why is it equal to 0? I have 8 RA because RA 8 is the distance from B. Minus 9 times 8 times 4. That's half of the distance from B. You know. Then plus, because that one is turning the same way as RA. Then about B plus 4.8 times 4 equal to 0. Equal to 0. So with that, I got RA. I got RA equal to 33.6 kilonewton. RA is equal to 33.6 kilonewton. RA is 33.6. I got RA equal to 33.6 kilonewton. 3.6 kilonewton. So I now come again to get RB. To get RB, I have total moment about RB is a moment about A is equal to 0. Is equal to 0. I take moment about A. So I can start from here anyhow I like. Okay, minus 4.8. Because I want to make RB positive. So 4.8 would be negative. 4.8 times, that's 12. 8 and 4, that's the distance from A. Then plus, because I made this negative, this is positive. So plus 8 RB, other one. Then the load, you know, then the load. The load minus 9 times 8. That's the whole load. About RA, about point A times 4. That is half of 8. Equal to 0. Because all the loads have been there. Equal to 0. Equal to 0. So I now have RB. RB is equal to 43.2 kilonewtons. It's equal to 43.2 kilonewtons. RB is equal to 43.2 kilonewtons. 43.2 kilonewtons. So what is it? 43.2 kilonewtons. So I have gotten the two reactions. I've gotten the two reaction A and reaction B. The next thing for me to do is to get the bending moment. The bending moment at this point. Let me call this H at point H. M at H is equal to RA. That's 33.6 times the distance, which is 4. 4 minus the load, which is 9, times the distance in this case is 4, times half of it, which is 2. That will give me the bending moment at that mid-span. That's at H. Bending moment at H. And I got this 62.4 kilonewton, 62.4 kilonewton meter. That is the bending moment at the midpoint here, H. So with regard to AB, I've gotten the reactions, I've gotten the bending moment. Now I move to CD. Now to get CD, let me now get the reactions. I start. So let me get the reaction at C. So total moment at D is equal to 0. I have, if the moment of there is 0, I take this one. I have, because I want RC to be positive, I have minus 3.2 times, I'm talking about D, times this, times 12, 5 and 7. Times 12 minus 15. 15 times 9. Minus 15 times 9. Then plus, because RC is positive since the other ones are negative, plus 7 RC. Plus 7 RC. And I got RC to be equal to 22.77. 24.77. I got RC to be is equal to 24.77 kilonewton. So the next to deal with is to get RD. And for me to get RD, I have total moment at C is equal to 0, so that I can get RD. So if I'm getting that, I take from here RDs. I have 7 RD. Take a moment this way. 7 RD. These other ones are going the same direction. Plus 15 times 2. That's the distance of the 15 from C. Plus, because it's in the same direction, plus 3.2 times 5, that's the distance from C, is equal to 0. So I got RD. So I got RD equal to 6.57 minus 6 point RD is equal to minus 6.57. RD is equal to minus 6.57 kilonewton. If you look at it, when I send this over there, you give me minus. So my RD is equal to 6.57 minus 6.57. So that's the reaction. The reaction at that's the reaction RD. I've got an RD, I've got an RC. Now let me get the bending moment. The bending moment at the mid-span. Bending moment at the mid-span, the first point at this mid-span here. Let's call this I. So bending moment at I, M at I is equal to minus, because that's 3.2. Find the distance, which is 3. Is equal to this is 9.6 minus 9.6 kilonewton meter. That's the bending moment at that point. The next is to get the bending moment at point C. The next is to get the bending moment at point C. Bending moment at point C. Bending moment at point C. So to get bending moment at point C now, I have MC is equal to 3 points minus, for that matter, the moment is, what is the first one I got? M at I. What is M at? Okay, well, yeah. M at, that's minus 3.6 times 5 minus 15 times 2. 3.6, that is 0.1. This is 4 minus 4 minus 30. That's minus 34. Minus 34 kilonewton meter. Minus. This is minus 4. Minus 30, that is minus 34. So I've gotten the different bending moments. I've gotten the bending moment at this point, at that point there. Got the bending moment. So at D, there's no bending moment. At C. So I draw the bending moment diagram. I take the beam to draw the bending moment diagram. Before then, let me get the bending moment at this point, at this middle. Let me see, I call this I. Let me call this J. Let me get the bending moment at that middle. If I want to get the bending moment at that middle, I have a J. M at J. M at J is equal to a J here. J is half of 7, which is 3.5. That means 3, this is 5, and that is 8.5. That means minus 3.2 times 8.5. 8.5 minus 15 times 5.5. That is 2 plus 3.5. That's minus. Plus the reaction C. What is reaction C? We got reaction C somewhere. That's reaction C. Where did I get it? Okay, reaction C. 24.77 times 3.5. That's the moment. That's the moment at that point. That's the moment at J. That moment of J, I got it to be equal to minus 23 kilonewton meter. Minus 23 kilonewton meter. So now I draw the bending moment diagram. I've gotten the bending moment in all locations of the beam. Since I've gotten all the bending moment in all locations, I now start to draw the diagram here. This is the point. This is A, point A. Then at the middle of B, that is at this point, at the middle of B, H. I got bending moment at H, MH, okay. Yeah. So I draw the bending moment diagram. is a curve. Here is 62.4 kilonewton meter, that is plus. Then it moves to and comes back to the minimum diagram and comes back to this. And gets 0 at this point. Moves these are straight lines, they are not curves. This is the only one that's a curve. So at B, what was the moment at B? The mark B, moment at B. I have moment at B. Where did I calculate the moment at B? That's okay. I will not see anywhere I can. Okay. Let me write this 0, the moment at this between E and F, moment at G. There's moment at G. Moment at G is somewhere here. Okay. Because they, trying to make the board to contain everything, This is at C, when that C is at C, that's 24.77 kilonewton. This is 0. This moment at J, where is J? Where did I put J? That's the one here. The one here is moment at J is 23 kilonewton negative. Then this is the moment at G that is one of them here, So that's the Benny moment diagram. That's the Benny moment diagram, which has been seen. This is positive, this negative, this is positive, this is negative. That's the Benny moment diagram. So for me to draw the shear force, I had to clean off some of these things to be able to draw the shear force. But the shear force is clear. The shear force has been gotten. Let me put down the shear force. Let me get this out so that I draw the shear force, even though some of the moments will be cleaned off. But I have to do that because of so the shear force diagram now. Shear force is the sum, the algebraic summation or vectorial summation of the forces from reaction A. From reaction A, the shear force is this. Reaction A, we got reaction A to B is 33.6. RA was gotten as RA was 33.6 kilonewton. That's the shear force. From there it moves RA because it was a UDL. Then we'll have reaction B here. And reaction B steps up and moves to 4.8. Maybe I should reduce this so that it can enter. This should be higher, yes. this point. This point. It's just removal of the subtracting the forces. 1.8, 1.8, this 3.2. Increases 6.57. That's the shear force diagram. So the bending moment diagram and the shear force diagram. So here we have been able to deal with this beam A, B, E, F, C, D, which would have been ordinarily have been an indeterminate beam, but because of the two hinges, it became determinate. So we solve it as a determinate beam by breaking the beam at those points of the hinges. We broke and got this. We have this, and we have this. Three breakages. Look at them here, here, and here. And we solved them, each of them. After solving the action we got here, we loaded it on this. The one we got here, we loaded it on this. Solve this, solve this, solve this. And that's what yielded this. We got the reactions, we got the bending moments, we got the shear force, and draw the diagrams. So, and that is the solution of this beam. So this beam now is ready to be designed. The stresses in the beam has been gotten because the stresses that you get that you're going to design against. And if you don't analyze this beam like this to get these stresses, you can't design. You can't design because you cannot arrest what you don't know. You have to. The design will produce material, will produce structure that will arrest the stresses on the structure in the form of load and actions. So this has given us values that we're going to design against if we want to design this beam. That is the end of this episode.